So like we've been discussing, we have our linear, quadratic, and exponential models. And now we're going to put this all together to think about real life situations. So in reality, models never perfectly fit the data. There is always some error. We can use what we have learned about the models so far to judge what would be best in each situation. This is called regression, choosing the best model. Okay, so we're going to be choosing between linear, quadratic, and exponential. To help decide which model might be best to use when modeling data, we can look at the first and second differences and the common ratio. If we compare those numbers, we can see which numbers are best reflected, which ones are closest together, and that can tell us whether it's linear, quadratic, or exponential. We can also create a scatter plot for the data, and we can look at the correlation coefficient value of a regression model. So what the correlation coefficient is, it's a number that's between -1 and 1 to describe the strength of the correlation. Generally, the closer you are to 1 or -1, the stronger the correlation, and the more closely the data will fit the trend. So if it's exactly 1 or -1, the data will fit one of the models exactly. But if it's a number in between there, it's approaching being a good fit, but not exactly for all data points. Okay, so looking at this table of values here, we have time in seconds and voltage. So we're going to look at all of the differences and ratios here. So looking at the first differences, we're doing 7 minus 9 is -2. 5.2 minus 7, -1.8. 3.9 minus 5.2. 3 minus 3.9. And 2.3 minus 3. Okay, so what we notice with our differences, our first difference here, is that none of these are the same. Okay, these are spaced out between -2 and -0.7. So let's look at our other ones. So continuing into second differences, we're doing -1.8 minus -2. This is 0.2. -1.3 minus -1.8. 0.5. -0.9 minus -1.3. This is 0.4. And -0.7 minus -0.9. This is 0.2. Okay, so here we see that we still don't have our matching numbers, but it is a little bit closer than what we have for our first differences. So here we're going between 0.2 and 0.5. Okay, so the first one we were going between -2 and -0.7. This one we're going between 0.2 and 0.5. Okay, so there's less of a difference within the differences there. And we can also look at the common ratio. So this would be 7 divided by 9 gives us 0.78. And 5.2 divided by 7 0.74, and then 3.9 divided by 5.2, 0.75, and 3 divided by 3.9, we get 0.77, and then 2.3 divided by 3, and we get 0.77 again. Okay, so here, again, we notice that the ratios aren't the exact same, but it's even closer than with our second differences. Here we're going from 0.74 to 0.78. So there's not much of a range in our ratios here. So because the smallest difference is with our common ratios, then we can say the regression model is exponential. That is the best fit for the data. So our exponential is our best model. Okay, so again, like we said, in real life scenarios, we're not going to have an exact fit at all times, but we're looking for closest to. So the closest numbers together are is the exponential data there. Okay, so the exponential is the best model. And we can remember when we're talking exponential, that is y equals ab to the exponent x. Okay, so to make our equation, y equals a is what we start at. So at time 0, we are starting at 9 volts, so we're starting at 9. And our growth rate, we're going to be using our common ratio. And because we have between 0.74 and 0.78, we can kind of find the average there. So halfway in between there is 0.76. So that's what we can use as our growth. And x will be our time. So the first one is we want to predict the tire pressure after uh, 12 seconds. So we're going to put 12 in for x. So 9 times 0.76 to the exponent 12. Okay, exponent first, 0.76 to the exponent 12, and multiply that by 9, and we get 0.33 volts. And after 45 seconds, we're going to say y equals 9 times 0.76 to the exponent 45. So 0.76 to the exponent 45, and then times 9. That's going to give us 0.000038 volts. Okay. So like our page before said, we can use our table of values and look at our first, second differences and our common ratio, or we can graph the data. So this next one here, we're going to use Desmos, and we're going to put in our table of values, and there's a way to have a line of best fit in each scenario, and that's with using these formulas. So for linear, we have our y1 is approximately equal to the mx1 plus b. Quadratic, we have the formula there, and exponential, we have another one. So we're going to be putting all of these in and seeing which one fits the data best. So I already have all of this inputted in Desmos, but I will show you a couple things in Desmos here. Okay, so I already have my table of values, but if you want to make one, you're going to hit the plus sign, hit table, and then you can input all the data. Go to the next line and you can type the linear equation. Going to the following line, you can type the quadratic and then the exponential. So I have all of those in there. And we talked about our correlation coefficient, that's R. So in Desmos, it calculates this R value for you. So we notice, I don't know if I can highlight this or not. Okay, I'm going to kind of highlight where it's located. So the correlation coefficient for linear is R equals negative 0.98. And like we said, the closer that it is to 1 or negative 1, the stronger the correlation is. Now looking for quadratic, we see that R squared equals 1. If we rearrange that, we would have the square root of 1, which is still 1. So R equals 1, and that's the strongest we can have. So that is, our quadratic is stronger than our linear. And if we look at our exponential, our R squared equals 0.9981, the square root of that. We still have our quadratic being the strongest with a 1. Like I said, the 1 is the strongest you can possibly have. We can see how this looks as we put each of the lines in. So right now I have it blocked where you can't see. But if we click linear, it's going to put our line of best fit here. We see that it's going through most of the points, but it's not hitting them exactly. So that's where we don't have that correlation coefficient being 1. It's not hitting exactly each point. Now if we go on and look at the quadratic, we notice here that the quadratic, this line is going perfectly through all of the data. So that makes sense with the correlation coefficient being 1. And if we move on to the exponential and look at that one, this one fits pretty nicely as well, but not as exact as the quadratic. So we are going to pick the quadratic model as our best fit here. Okay, so we're going to pick quadratic, and that is because our correlation coefficient, our R, is equal to 1. Okay, and it goes through all points exactly. Okay, where the other ones are a little bit off. Now it's going to ask us, what is the height of the hole in the bottle? So we need to look, and we're talking about water level here, and we want to know where it's going to stop draining basically. So as low as we can get the minimum value. So you can always adjust the axis. You can zoom in, zoom out, whatever you need to do. And what we notice, because it's quadratic and it's opening upward, then there is a minimum value that we get to before it starts going up again. So we want to find that minimum value, and that's what we're going to use. Okay, so it kind of creates a minimum value for you, which is around here. And so looking at the Y value for the minimum, it's about 5.2 centimeters. Okay, so since that's the minimum, that will be the height of the hole in the bottle. So the minimum point and that's at 5.2 centimeters. And this was based on the Y value. I'll include that as well. Okay. So you have options whether you are using a graphing calculator and you are approximating based on using all these formulas for a line or curve of best fit, or you have your table of values, you're looking at your first, second differences and your common ratios. Those are the options for your regression models. Okay, so you're going to be given a worksheet, and just let me know if you have any questions.